Okay, so review from yesterday. We had Hooke's law. Okay, Hooke's law tells us that the restoring force in any elastic object, but a spring specifically, okay, is equal to negative k times x. All right, so that is the spring constant times the displacement of the object from the resting or equilibrium position. Okay, and that negative sign is there to make sure that the force is always opposite in vector from the displacement. Because if I displace something to the left, okay, then the spring has to pull to the right or push to the right, whichever it is doing. Okay, so that's what that negative is there for. Okay, we also went over yesterday how this force in a spring is related to elastic potential energy. Okay, so we get elastic potential energy by exerting a force on the spring through a distance, by doing work. Okay, everyone okay with that? All right. According to Hooke, the force we're working against is this one. Okay, but if we're increasing that force, we're not always using the maximum force. We're using the average force, which occurs in the middle. Okay, so this is actually in the formula written as average force. So the average force would be 1/2 of k times x. And then the distance would be x again. Okay, and if I have 1/2, or the average force, multiplied by the distance, I end up with the formula for elastic potential energy, which is 1/2 kx squared. Since energy is scalar, okay, that negative is unnecessary. Okay, everyone follow me there? Okay, that's kind of where, that was the new stuff kind of from yesterday. Okay, and then from there, we went into law of conservation of energy, which is not new. Okay, we've done law of conservation of energy problems in Unit 2 to do with roller coasters. The only thing that changes for this unit is instead of having gravitational potential energy, a mass spring system has elastic potential energy. So we use that in place of MGH. Okay, and then everything else works the same as it has before. Okay, is that ringing a bell from yesterday? Yes? Okay. All right. Now, the thing we didn't talk about with Hooke's law yesterday, okay, is something that's happening in question number 1. Okay? In question number 1, we are given a mass, and we're told it's on a horizontal, frictionless surface, and that the mass is oscillating back and forth. So if it's on a horizontal surface, and that surface is frictionless, what is the only force causing the mass to move back and forth? The restoring force, exactly. Okay? Since the restoring force is the only force that is present, it is then by default the what force? Net force. Net force, exactly. Okay? So we would say in a situation where we have an oscillating mass on a spring, okay, that negative k times x would equal m times a at any point in the oscillation. Whatever x is, the acceleration would be different at every x. Okay? If I go further away from equilibrium, a would get bigger because the restoring force would get bigger. Okay? If I was closer to equilibrium, a would be smaller because my restoring force would be smaller. Everyone okay with that idea? Okay? So if we're dealing with a situation where it's especially a horizontal, frictionless mass on a spring system, then the restoring force is the net force. What Hooke did in his experiment was he hung the spring from the ceiling and didn't let it oscillate. He just put the mass on it and kind of lowered it slowly until it didn't fall any further and said, okay, negative k times x equals m times g. Okay, which was fine. It was gravity that was causing the spring to pull upwards, to have a restoring force at all. Those forces would be equal. Okay? In that situation, what is the net force? The mass is just hanging there from the ceiling on the spring. 0, exactly. Okay, so it would still be a sum of all forces thing. Negative k times x plus mg would equal 0. Those two forces are equal but opposite. Okay? So those are the situations that you can encounter with Hooke's law. Okay, this one in particular is dealing with that situation. Okay? Question number 2, okay, is actually a law of conservation of energy question. So I would like you guys right now to try questions 1 and 2 and see if you can solve them, knowing that this is a Hooke's Law question and that this is a conservation of energy question. Okay. Give you a few minutes on those. Okay, so on number 1, it's in a lot of these questions really important to visualize the context of the situation. Okay, so this mass is attached to a spring and it is moving. Okay, it's accelerating, oscillating back and forth. Okay, we're looking for the mass's displacement when its acceleration is 4.11 meters per second squared to the left. So where is this object, right or left, given that number? Right. It's right. Okay? Because the acceleration always acts back towards equilibrium, and the only way you can accelerate left and have that be back towards equilibrium is if you're right of equilibrium. Does everyone follow me there? Okay? So I kind of have to keep that in mind when I'm setting up this equation so that I've got this situation here. Okay, so I've got negative k times x equals m times a. I know it's the net force in this situation because the only force acting is the restoring force. It's horizontal and it's frictionless. Right? So I'm trying to find x. I'm trying to find the displacement. So when I manipulate for x, I'm going to divide both sides by negative k. I want to bring that negative over with me. Right? Now, just in order to make sure I get the vectors right, I'm going to make left positive. Okay, so I'm just going to have that 4.11 be positive. So when I plug in the numbers, I'm going to have 0.724 kilograms times 4.11 meters per second squared divided by negative 8.21 newtons per meter. Okay, when I do that, I should get the 0.362 meters, but on my calculator, it will be negative. The opposite of left is right. Okay? I got a negative number when I assigned positive to left, so that means that it must be right. Everyone all right with that? Okay, so it's important to keep those directions straight when you're doing this because vector will be part of that. And if you don't have the correct vector on your answer, you'll lose a mark for it. All right, how are people doing on number 2? Okay, do we still need a little more time on number 2? All right, I'll give you a little bit more time on number 2, and then we'll have a look at it. Remember, it's a conservation of energy question, okay? So that means, just like the roller coasters, EI equals EF. Now, here's the tips I will give you for this question. The term amplitude means that's the furthest point from equilibrium that the object will reach. Think about how fast it's going at that point. The spring has been pulling it back towards equilibrium the entire time, and then it gets to the maximum distance. It's kind of like the maximum height you could throw something to, right? And then think about where the maximum speed, which is what you're being asked to calculate, is going to occur. Okay? Where in the oscillation does the maximum speed occur? And if you are at your maximum speed, what kind of energy do you have? Okay? Those would be my tips for that question. Okay, let's have a look at number 2. So in number 2, we've got an object that's oscillating back and forth with simple harmonic motion. Okay? We know the spring constant of the spring. We know the mass of the object, right? And we're told its amplitude, which is the maximum distance from equilibrium. That happens in both directions. Okay? So this distance right here is 1.12 meters to the left, and this distance here is 1.12 meters to the right. The object is behaving exactly the same way, regardless of which one of those two positions it is at. What is it doing at each of those two positions?
Trying to get back to equilibrium.
Okay, trying to get back to equilibrium, which would actually be true anywhere not at equilibrium, but it would also be true at those positions. What is unique to that position?
Oh, is it at rest?
It is at rest, exactly. Okay, all the way to either of these positions, the restoring force has been accelerating the object back towards equilibrium, which means it's been slowing it down in the same way that would happen if you threw something up in the air. Gravity would first slow it down and then would bring it back. Okay, so at this position here, the speed is 0. And the spring is stretched or compressed as far as it can go, which means the only kind of energy that is present at that position is what? Potential. It can't have any kinetic because it has no speed. Okay? So at this position, at a position of maximum amplitude, we only have potential energy. Now, I wrote A, not X, because A is a special X. It's the maximum value of X. Okay? Here, at equilibrium, is where my maximum speed occurs. And at that position, the spring is neither stretched nor compressed. Its displacement, or X, is what at equilibrium? 0. That means it can't have any kinetic energy, because in the kinetic energy formula, we're multiplying by X. And if we multiply by 0, we get 0. Okay? Plus, at equilibrium, the spring can't push or pull, so there can't be any potential energy stored in it. So, at this position, we only have kinetic energy. So this question is basically just like if I told you a roller coaster is at rest at the top of the highest hill, figure out how fast it's going at the bottom when it's at ground level. That's what this question is, but it's from a mass on a spring perspective instead. Okay? So I would set it up as a conservation of energy question, saying that my initial energy, okay, would be EP initial plus EK initial equals EP final plus EK final. Okay? But right away, I know there's none of that and none of that. Okay? So what I'm left with is the maximum potential energy equals the maximum kinetic energy. Everybody okay with that? As I said, it's like the top of the highest hill and the bottom of the roller coaster. All right, so now I should be able to manipulate to find the maximum speed. The halves are going to cancel when I move them over, and then I'm going to divide both sides by m, and then I'll square root. So what I'll be left with is that the maximum speed is the square root of k, which was 4 newtons per meter, times the mass, which, or sorry, times the spring constant, sorry. No, that is the spring constant, sorry, times the displacement, 1.12 meters, that's right here. Squared divided by the mass, which is 0.05 kilograms, because they gave it to me in grams. I can't use grams when I'm calculating joules, because a joule is a kilogram meters squared per second squared. Okay? All right, when I plug all that in, I should get 10 meters per second as my speed at equilibrium. Okay. Does that make sense? Kind of ring a bell on conservation of energy a little bit? Okay. All that's different is we have a different kind of potential energy. Okay. Other than that, it's just algebra. It's the same algebra we did before. All right. Okay, so this is a trickier question. It has 2 parts. I wouldn't ask a question this way because it makes it seem like you should be able to do it in one step, and you absolutely can't. Okay? If I was asking this question, I would ask it in 2 parts. I would say in part A, calculate the mass, and then calculate the period. So this is a 2-part question. You're going to have to do one conservation of energy calculation to get something that you need to calculate the period of the mass on the spring. All right, so the thing you need to remember is that the period of a mass on a spring is dependent on the mass and the spring. And there's something in that formula you don't have that you could get with another calculation. Give you a few minutes on that. All right, so what I need that I don't have is mass. Okay, they don't tell me that in the question anywhere. They tell me the amplitude, they tell me the maximum speed, and they tell me the spring constant. Okay, but they don't give me mass. So I can't use amplitude and speed in that formula, but I can use amplitude and speed in a law of conservation of energy problem. Especially if I remember that at the maximum amplitude, I would only have potential energy, and my maximum speed occurs when I only have kinetic energy at equilibrium. So those two things would be equal, just like we did in the last question. Right? I have the maximum speed, I have the spring constant, I have the amplitude. The only thing I don't have is mass, and now I have the ability to get it because it's the only thing I'm missing. So I'm going to manipulate for m. That means dividing both sides by Vmax squared. Okay? So that'll solve for m. So m will be 5.03 times 0.1225, because they gave it to me in centimeters, and it needs to be in meters, and that has to be squared, and then divide that by 5.13 squared. Okay. So if I do that, I get like a really tiny mass. It's like 0.0026 or something, or 28. 28? Okay, kilograms. So it's like just a little less than 3 grams. It's very small. Now that I've got that, now I can go up to this formula. All I have to do are plug in the numbers because now I have both m and k. Okay, so when I do that, oops, sorry, forget about the 2 pi part there. Okay, times m, so 0.0028, okay, with all the decimals obviously, divided by the spring constant, which was 5.03, and when we do all that, we should get 0.15 seconds for the period of that oscillation. Okay, because this is like a reasonably heavy spring with an incredibly small mass on it, so it's only going to like vibrate a little bit back and forth. Okay, it's not going to have a huge oscillation. Okay. All right, everybody okay with that? Yes? Okay. So, questions at all? The law of conservation of energy stuff making sense? Okay. Hopefully it's familiar. All right, so question number 1 is the one I want you to work on next, and it is going to ask you to do everything we've done in this unit thus far. Period, Hooke's law, and conservation of energy. It matters not which order you do it in. You can do A, B, and C first if you want. Okay, it doesn't matter which one you do, you have the information to do them all. One of them does not depend on a calculation of the other. So in 1A, it's a Hooke's law question. We're asked to find acceleration. Now, the thing about Hooke's law and law of conservation of energy is they often give us very similar pieces of information. And sometimes it can be tricky to tell which one it's asking. Okay? So here's what you need to look for. In a law of conservation of energy problem, they have to be comparing 2 positions in the oscillation. Okay? Otherwise, you can't do EI equals EF. You have to have information about 2 positions within the oscillation in order to compare them. Hooke's law may involve an object that is oscillating, but it's only going to ask you about one spot, like this one does. Okay? In 1A, it says, what is the acceleration at a displacement of 0.3 meters? It doesn't say, oh, and by the way, there's this other stuff going on. It just asks, what's the acceleration at this spot? Okay, does that make sense? Will you ever be asked to calculate speed in a Hooke's law question? Never. It's not part of it, right? It's either negative kx equals m times a, or it's negative kx equals m times g. There's never speed involved in that. It's forces. Okay? So look for those kinds of things. Look for forces. Look for 2 points within the system, things like that, because they can tell you a little bit about, oh, you need to solve this one using Hooke's law or this one using law of conservation of energy. Okay, since this one's only asking about one position, okay, I know it's a Hooke's law question, so I'm going to say that negative k times x equals m times a. Okay, they did say it was a horizontal spring. They'll imply it's frictionless. Right, and now I'm going to solve for a. So I'm just going to divide both sides by m. Okay, and then plug in my number. So negative 40 times 0.3 divided by 2.5 should give me negative 4.80 meters per second squared. Okay? That needs to be negative because I have to assume that displacement was positive because they didn't give me a direction on it at all. Right? So all I can say is the acceleration at that point is opposite. Opposite would be negative. All right? Everyone okay with A? Okay. Part B is your law of conservation of energy question. Maximum speed. Okay, well, I only ever solve for speed with a law of conservation of energy problem. Okay, I never use Hooke's law for that. So right off the bat, I know this is an EI equals EF kind of question. Okay, I'm going to deal with the point they gave me, the maximum amplitude, and the point they want me to find. Okay, the maximum speed, which occurs at equilibrium where there's no potential energy. Everyone okay with that? Because I mean, I should technically have written 1/2 mvi squared equal, or plus this, and over here I should have 1/2 kx, but there's 0, so I didn't bother to write them. Okay, so I'm looking for V max, so I'm going to divide both sides by half of m. The halves will cancel, okay, and I'll square root to get V. So the maximum speed will be the square root of 40 times 0.8 squared divided by m, which was 2.5. Okay? The most common mistake I see in conservation of energy problems is people forgetting to square the displacement. They'll always square the speed. They'll always remember that, but they forget to square the displacement. Right? So when we do that, we should end up with 3.20 meters per second as our maximum speed occurring at equilibrium. All right, questions on that one? Okay. So the only way a law of conservation of energy question gets more involved than that is if they ask you, here's the maximum amplitude, find the speed at this displacement, where there would be some potential energy. It would be like, here's the top of the hill where you're not moving, calculate how fast you're going when you're halfway down the hill at this height. So you'd still have some potential energy and you'd have to subtract it over. It's still like a roller coaster question. All right, for part C, that one's just plugging into the period formula. Okay, so T will equal 2 pi times the square root of m, which was 2.5, divided by k, which was 40. So when we do that, we should get 1.57 seconds as the period. All right, everybody okay with that? All right. Try number 2. I'm not going to tell you what kind of question it is. You got to figure it out. Okay, what kind of question is number 2? It's a Hooke's law question, yeah. Okay, and we know that because they're giving us the acceleration, and the only kind of question we ever get acceleration in is Hooke's law. Okay? We can't get acceleration really in a law of conservation of energy question because it's always changing as it oscillates. This is asking about one position, and the acceleration at that position is this value. Okay, so we're going to have negative k times x equals m times a, right? We're looking for k, so I'm going to divide both sides by negative x. Right, so k will equal 20 meters per second squared times 0.0026, okay, times 20 divided by negative 0.7. Okay, and what should I make sure of here that I haven't done yet? Because if I do this the way I have it written, I'm going to get a negative number for k. Can k be negative? No, it's an absolute value. So I need to recognize that I divided by negative x. That means that x is positive here. Well, that means this has to be negative, because the acceleration and the displacement are always the opposite vector. Okay? I brought the negative over with x, but x was a positive number. Okay? So if I make that negative, now it'll work out sign-wise, okay? And I'll get that my k is actually a positive value of 0.0743 newtons per meter. That is an incredibly light spring. Okay, like it would blow away in the wind, light. All right, questions on how those worked? Okay, one more I'd like you to try here before the end of class. That one. Okay, I want you to try that one. Okay, what kind of question is it? It's a Hooke's Law question. It is, in fact, exactly like Hooke's Law's experiment, right? He hung a mass from a spring. Well, they just told us not the mass, but the weight. And in Hooke's experiment, it was weight that was equal to the force in the spring. Okay, so we already know that weight. Listening, please. 9.3 newtons and negative k times x. So all we have to do is solve for x by dividing both sides by negative k. So what was it, 25 newtons per meter. Okay, and since this is down and the spring force is up, I'm going to make it negative as well. Okay, which will give, sorry, I'm not going to make it negative. That'll give me an x that is down because my spring force is actually up. Okay, everyone follow me there? All right, so we do that and we'll get our 0.37 meters.
Please rise and remain silent.